ready. Share my screen.
Awesome, we can see your screen. Thank you.
So in this talk, Mandeep and I are going to introduce the front-end support in the FlexFlow. And my name is Wei Wu, and I'm a research scientist at Los Alamos National Laboratory, and Mandeep is from Facebook. First, let me show the overview of the FlexFlow structure. The FlexFlow is built on top of the Legion runtime. Legion is a task-based program system developed by researchers in Stanford University, NVIDIA, and Los Alamos. The major component of the FlexFlow is the FlexFlow runtime, which is developed with the C++. And on top of the runtime, we have this orange bar called mapper or parallelizer interface. It allows users to provide any customized parallelization strategy in the SOAP search space. In addition to it, the FlexFlow can also automatically search for optimized parallelization strategy, which will be covered in the next talk. In this talk, Mandeep and I will talk about all these FlexFlow APIs and how to use them to create and train a model. So this is the outline of this tutorial. I will talk about the native Python API, Keras, and PyTorch support. And Mandeep will introduce the ONNX support. So before going to all type of Python APIs, I will briefly introduce the design of the FlexFlow Python integration. The FlexFlow runtime is developed by C++, and the Python API invokes the C++ API via the Python CFFI library. So the Python API is a very thin layer, and you will get a similar performance as if you are using the C++ API. With the Python API, we also provide an interaction with the NumPy arrays. So people can map a NumPy array to a tensor in the C++ side. Different from the Keras and PyTorch, we do not use the native Python interpreter. Instead, we use the Python interpreter provided by Legion. Let me show you an example to explain what does it mean. So this is the command line of running a FlexFlow Python program. And in this red rectangle, we are not using the Python binary. Instead, we are using a binary called FlexFlow Python. It is a Python binary together with FlexFlow and Legion runtime. And the Legion runtime will manage the Python interpreter and assign a CPU core to execute Python code. So once the Python API invokes the C++ API, the FlexFlow runtime will launch tasks for computation, and the Legion runtime will distribute this task to either CPU cores or GPUs across the machine. So even if people write a sequential Python program, the FlexFlow can also automatically extract parallelizations through the sequential syntax. Now, let's take a look at the native Python API. First, you will need to import this Python module, and the FlexFlow takes the program model of the Legion. So we take this notion top-level task from Legion, which is where the user level code starts from. Then let's look at how to create a model with the FlexFlow Python API. The first step is to create a FlexFlow model. Before initializing a FF model instance, you will need to create this FF configure. That is the configuration of running model, such as batch size, number of GPUs, and other configurations. You need to provide them in advance because the FlexFlow runtime need to know these configurations to figure out how to parallelize the model. The second step is to create input tensor. In the FlexFlow, the tensor use the NCHW format. Also, it's called the channel first. because this kind of format is optimized for GPU. And the last step is to add operators to the model. This is the example of convolution 2D operator. So no matter what operators you are using, the first parameter is always the input tensor, and the return value of an operator is always an output tensor. Now we have a model. Then we need to initialize the model to create the data loaders before training it. And the first step is to compile the model. The reason of using this compile function is FlexFlow is using the lazy initialization. So which means when adding operators into the model, we just create metadata. So in the compile, we will allocate all the tensors and parameters of all the operators. And we'll also do a lot of optimizations during the compilation of the model, such as automatically finding the best parallelization strategy and model fusion. In the second step is to create data loaders. We take the NumPy array as the input of the data loader. So once the data loader is created, the next step is to initialize all the operators or layers of the model using the given data loader. After the model has been initialized, we can train the model. The easiest way is to use this fit function, which is similar to the fit function in Keras. Or people can implement a customized training procedure using the built-in functions of FlexFlow, such as forward, backward, and others. Now I have done the introduction of the Python native API. It is pretty straightforward to use it to create and train a model. Now I'm going to talk a little bit about the C++ API. For convenience, we make the Python API identical to the C++ API. Here is the example. So if you compare the top and the bottom code, they are almost the same. They have almost the same parameters, except some differences in syntax. So if you are a C++ guy and you would like to trick the FlexFlow runtime, you are welcome to try the C++ API. This slide shows all the operators that are supported by FlexFlow. If you need more operators, feel free to let us know, and we will implement them for you. Now I'm going to introduce the Keras support. By the way, we will also provide a demo to show how to run a Keras and a PyTorch model with FlexFlow later in the hands-on exercise. Here example of a Keras model. In order to run the model with FlexFlow, you only need to change the import Keras to import FlexFlow Keras. Usually there's no change on the model itself. So it should be very easy to use FlexFlow to train existing Keras model. But one thing to make sure is sometimes Keras using the channel last format for tensor. In that case, you have to change it to channel first. Now let's look at the PyTorch support. For the PyTorch support, we do not reuse the Keras solution. It is because the PyTorch allows dynamic construction of the model, which is not the program model of the FlexFlow. And the FlexFlow performs a static model optimization after the entire model is created. The optimization happens during the compilation of the model, and it includes several optimizations like finding the optimal parallelization strategy and model fusions. And we cannot do such optimization without an overview of the entire model. So in order to support a PyTorch, we use a new feature of the PyTorch called TorchFX. The FX module is able to convert a PyTorch model to a graph representation. Then the FlexFlow is able to iterate the graph and reconstruct the model with the FlexFlow API. The ONNX support is also taking a similar approach. Now let's look at an example. Here is a PyTorch model. People can use this torch to FX function to output model into a file. The file contains the graph representation of the model. Then let's introduce how to import this model into FlexFlow. I've showed this example before when introducing the Python native API. Now what we need to do is to replace the model creation code with the model import code. With these 2 lines of code, we import the PyTorch model from a file and convert it into a FlexFlow model. I'm done with the talk, and Mandeep will talk about ONNX support. Mandeep, are you there?
Yep.
Okay.
Hi, I'm Mandeep. I'm going to be talking about ONNX support in FlexFlow. So ONNX is a graph intermediate representation. It has a very large community of support. PyTorch has native support for exporting to ONNX, and there are converters available for other deep learning frameworks such as TensorFlow. To use the ONNX support, you need to install the ONNX Python package, and you need to ensure that FlexFlow is built using the same protobuf library as was used to build the ONNX Python package. So I'll show how ONNX export works in PyTorch. You simply take your model, create a sort of template, and then you call torch ONNX export, specifying the output file name. You can find more information in the PyTorch documentation. To import an ONNX model, there's the FlexFlow ONNX package with the ONNX model class. You import your model using the same file name you use to export from PyTorch, and then you can apply your model using calling the apply method on the ONNX model. ONNX support is still work in progress. Patches are welcome. With that, I'll leave it open for questions.